Thank you. Good afternoon, everyone, and thank you to the organisers for allowing me to come down here and give a talk about the robotics work that we have been doing. The organisers asked to kind of give a bit of an overview of the activity and what's been going on, also as well as some of the future directions. So it's going to touch between technology and, unfortunately, maybe a bit of academic talk as well that's going to come through. I'm going to start with drones because it's one of the first pieces of work that we did. This is almost 15 years ago now, and one of the first projects that we had was with Land and Water Australia, and it was to detect aquatic weeds using drones over large areas. And this was a time before drones were called drones. There was no such thing as drones back then. You couldn't buy them off the shelf or anything like that, so you had to do everything in the lab. So we bought a remote control helicopter and we put our own autopilot system on board. This little steel box that you see out the front there has a camera system and a computing system on board, and we had to just basically fly over large amounts of area, mainly around creek beds and things like that, and try and look and detect aquatic weeds. One of the first, that should say pattern recognition, not pattern recognition. One of the first things that we had to look at was algorithms that could detect patterns in the data. And you probably hear it nowadays as machine learning and AI and the kind of use of that technology. But one of the first things that we had to look at was how do you detect weeds amongst all this type of clutter that you see there. And one of those first algorithms was known as support vector machines. It was a very new algorithm at the time. It was popular amongst the computer scientists. Engineers didn't touch it as much. But when you came through, you could actually start to look at things such as colour and texture and shape. And the algorithms would just kind of look at all the colour data, texture data, shape data, and try and identify certain features. And then you'd come along and say that was a weed and that was a weed. And I'll talk a little bit about that later. But this was the kind of one of the first trials that we had. We're not spraying any herbicide here. You can imagine trying to spray herbicide along a riverbed and getting it all red and wrong and all that stuff was going to be problematic. But the thing was kind of flying around, detecting weeds, and then positioning itself and then spraying where the weeds were. This was just water at the time, just spraying water. So we're probably adding to the weed problem at the time. But it was just spraying, and it was a very hard problem. And one of the most difficult elements of all this is that you had a lot of downwash that was happening from the rotor blades coming down, and so the water that you were spraying, and hence the herbicide, eventually would just kind of go everywhere, right? Which was problematic. So then, how do you position yourself? Understanding wind effects and where to spray was an important element. It was actually not too much of a problem as well, in the sense that one of the issues was trying to get spray underneath the waxy levels of aquatic weeds. So the aquatic weeds on the top would have a lot of wax, and so even if you sprayed herbicide, you couldn't kill the weed. You'd actually have to ruffle up the leaves, and that was pretty good in terms of the downwash. Downwash was doing that, and the weed spray would go underneath. Then we moved on to Meat and Livestock Australia funded us for about 3-4 years, looking at detecting woody weeds across large landscape areas. And so this was, again, an off-the-shelf aircraft, and then put our own autopilot system on board, a camera that would look down, and you'd fly over. These was about 5 by 10 kilometre areas, and just fly over these large areas, basically to do some transects across there, build up very accurate maps of what the environment would look like. And this was some better machine learning algorithms now. So the first one that I showed you there, we had to run that overnight in order to make that work. This one here we could run for about 4 hours, 5 hours on a desktop computer. And all the different colours there are the algorithms detecting different types of native vegetation from woody weeds and being able to isolate out those weeds. And then some funding from the Australian government, which was looking at the northern tablelands in New South Wales. And this was combining satellite data, high altitude aircraft, and also drones, and kind of fusing all that information together. And now we could process the data within about half an hour over large areas, right? So you can start to process data, get all the satellite imagery, and then start to infer where you thought the weeds were as you were going through, and start to pick out where all those weeds are. And that was really good. So we got these drones now flying and satellite information, fusing all that information to detect all the weeds. The next steps were, well, what do you do about the whole process? And that started to kick off some work in terms of taking the algorithms and then putting them onto ground robots. And then from the ground robots being able to not only detect the weeds, but then being able to do something about those weeds. And so I'm just going to slightly deviate here. There's a lot of activity already in automating vehicles. I wouldn't call them robots. They're just kind of platforms, you throw some GPS. And in the grains industry or broadacre industry in general, it's quite an easier problem, in quote. It's flat land, open skies, you can use GPS and you can just go from there as you're going through. And so there's many different examples up there of different techniques. But as a roboticist, when you start to talk about ground robotics and doing weed detection, and you want to start to apply the algorithms, what you're really trying to do is some real-time movement in a terrain and being able to detect where the weeds are and spraying the weeds. And this is just an example of the project work with Meat and Livestock Australia as well. And you've got an undulating terrain now. You've got logs, you've got rocks, you've got ditches, you've got moving animals. And so somehow you've got to have an agile platform. In this particular case, it's a four-wheel drive, four-wheel steel platform. It's about 150, 180 kilos, depending on the payload capacity. It can move at centimetre accuracy and all the way up to about 21 kilometres per hour. So it has a very precise control all the way up to very fast speed. It's also got a little pivot point right through here, which means that we can always maintain 3 wheels on the ground while it's going over logs and rocks and things. It's almost like a Mars rover, but kind of designed for terrestrial applications. Little actuator system that goes through there, and obviously computing in memory and all that. So the system, so as roboticists, you kind of think like systems engineers, and it's very much like what a farmer would think. You kind of look at everything, and you're trying to optimize a system and build the system according to what you need in that. The reason why I've labelled all those things around the robot is because you're seeing rapid advances in technology as you go through, and the reason why is any one of those individual elements there, whether they're sensors or communication systems or whatever it might be, is advancing every 3 to 6 months. It's just at a new level, and every time you get that advancement in that particular category, the robotic capability gets a lot better. And so all those things that I've mentioned on the right there, right, all the different bits and pieces that we look at robotics, is really about how do you take all these algorithms and make the robot smart. Right, so this robot now has to navigate across the terrain, avoid obstacles, avoid animals, avoid ditches, target weeds, spray the weeds with the right amount of herbicide and move on. So serrated tussock was a classic example. So this is now the robot running in real time. It's detecting serrated tussock in real time as it's moving through. It's avoiding any obstacles that it sees along the way. And then it goes through this process of visual surveying, which is basically, that's what I mentioned before about the four-wheel drive, four-wheel steer, being able to position itself and centre itself directly above the weed. And then it'll have this little manipulator arm that will come down and just spray the right amount of herbicide based on the size of the weed that it's got there, right? And so you're just looking at those two things and minimising how much chemicals you would be using along the way. And so you can basically give it a paddock and you tell it where the no-go zones are, and you just tell it to seek and destroy. And it doesn't have to follow a mowing pattern because it's looking out in front, so it's sampling out the space in front of it and saying, I'll go over here now, I'll go over there, based on the information that it's retrieving, right? And so it'll just move around and just spray as it's going through. So that's just kind of, I guess the reason why I wanted to show that was when we were looking at the problem, we're looking at what does the landscape look like, what are the type of weeds are, and then how do you optimise the right type of robot solution that's both robust and low cost, which is really what it came down to make it work. We've done the same thing in horticulture, and I'll show you the robot first. And this is Ripper. This is one of the bots that we built. It's a solar electric bot. This is just one of our trials where we demonstrated 24-hour capability of the bot, just going out there into the paddock and constantly going up and down the rows, and collecting information and spraying as well. So again, it's one of those things where you design the bot such that this had solar panels on the top, and you wanted the energy out, so how much energy was being pulled out of the wheels going through the terrain was equal to the amount of sunlight that was coming through onto the solar panel and turning that into energy. So it was an optimization problem, almost like a Formula One design kind of process. You were sitting there kind of optimizing everything from the gears and the wheels, terrain interaction all the way through. And the reason why you want that is because you wanted the battery to survive overnight, right, when there was no sun. So at about here in this particular case, 3 o'clock in the morning, the power went down, and just the next day the sun came up, it recharged in the first few hours, and off it went and moved through. So it gives you the capability of being 24/7 out there, and then you want to be able to design different types of tools to be able to look at different types of weeding technologies, right? So it's the same thing, detecting a weed from amongst the crops. In this case here, we've got a little robotic arm. We've just gone back to the good old days of, chipping and hoeing and whatever it might be, and just being able to remove the weeds. So it's detecting where the weeds are. What is the optimal plan for the arm to avoid the crop as it's coming through to remove it? In real life, you wouldn't be using a robotic arm. It's just too expensive in that process. So this is more of a lab trial. This is, again, the same thing, herbicide, but just dabbing it on the weed as you're going through. Again, how do you kind of do that in the right way? And just being able to drop a few drops of herbicide. And when you're dealing with small robotics, and you're dealing with, being able to do things precisely, you don't need to dilute as much of the herbicide. So you don't need to carry as much of a payload as you're going through. So we can carry a 50-litre tank and cover large acres across a farm because of the process not necessarily diluting it. One of the key technologies, there were two key technologies. This here is showing you a directed spray technology. So as the bot's moving in real time, I'll just run that again if I can. As it's running through, it's detecting each individual plant in this particular case, measuring the size and spraying the right amount of chemical on that plant. And also we looked at mechanical removal. So in a veggie industry process, it's quite simple. You can kind of detect the weeds across the crop as long as the crops are, not growing and overshadowing where the weeds are. So that's just showing you mechanical time, detecting where the weeds are and just scratching off the top layer of the weeds. And if this bot's going 24/7 up and down, then there's a lot of, then it's the capability of being able to remove those small weeds as it's going through. So I'm going to go academic and then come back to a grains example, right? Just I want to kind of talk about the building blocks that you're seeing that are coming through. So whether it's the weeding technology I was showing you, the bilberry guys are going to be talking next, you'll be seeing the same type of technology sitting through, and some of the other tech that you're seeing all the way through. There's two types. There's the machine learning algorithms, which are the pattern recognition algorithms, collecting large amounts of data and then trying to have these algorithms learn about colour, texture, shape, relationships between a weed and a plant, and then letting the algorithm learn that. And then there's the intelligent tools. Now, for anyone who's interested, end of last year there was a review that came out that was talking about machine learning in agriculture and just went through the whole process of talking about different algorithms as you're going through. There are key things. Lots and lots of data needs to be collected to make this work. And then you go through this exercise called labelling. So as an end user, you're hoping that you just get this system, and this system now works on the back of your tractor or on your robot or whatever it might be, and off you go from there. But the processes that have to happen, every time there's a new weed, or every time there might be a new soil to weed relationship or a plant to weed relationship, you potentially have to go through this whole process all over again, which is to collect large amounts of data. Then you go through labelling. Somebody sits there and goes, that's a weed, that's a weed, that's not a weed, that's a weed, that's a weed, etc., etc. And the algorithm then takes out that information and says, okay, what am I learning about colour, texture, shape about the particular weed in order to be able to kind of extract it from the environment. You train up what they call a machine learning model, and then that model sits on your weed device, whether it's a sprayer or it's a mechanical weeder or whatever it might be. And that model is kind of like the model that we have in our head. So if we've learnt what turnip weed looks like, because we've looked at colour, texture, shape over and over again, internally we have a little model that says every time I see something I see that as turnip weed, and it's the same thing here. You've trained a model and then that model sits on the back of the tractor. So these next two slides are going to go a bit intense, but I think it's important because when I talk about where to next, it's going to kind of touch on that. I've only got 2, maybe 3 slides of these boring slides, right? There are 3 types of machine learning algorithms that are kind of going out there at the moment now. There's supervised, semi-supervised and unsupervised. And what they say is what they mean. A supervised machine learning algorithm is one where, as a human, I'm sitting down behind 100, 200, 500 images and I'm going weed, 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 and then the algorithm learns what I've clicked on and what I've decided on. An unsupervised would be a great algorithm to have. It's just very computationally expensive, and so far at the moment now we haven't been able to solve it to run in real time. But an unsupervised algorithm is an algorithm where the machine's just going out there and the images are just being collected, and it itself is learning about differences in the environment and saying, I see something here which is different from there, and I've seen it over and over and over again, and I'm going to classify it as a blob, and I'm going to say that's something. Later on a human can come along and go, that's a weed, but the algorithm itself is learning the differences between there. And the semi-supervised sits in between, this ability to be able to kind of teach an algorithm and put some structure. For example, weeds only exist between the rows of the plants, right? So I put some structure in there, and anything that sits in between it is a weed. Everything in the rows is a lettuce or a grain or whatever it might be. So that's the first boring one. The second one is this one, deterministic, stochastic and temporal. All right. So you hear a lot about you won't hear anything about deterministic or stochastic or temporal algorithms. Usually most machine learning algorithms and weeds are in the deterministic space. In fact, most are called supervised and deterministic. Okay, which basically means a weed will always look a turnip weed or a ryegrass will always look the same no matter what. If I can go into stochastic, which means I'm adding some probability, it means actually ryegrass can change according to the soil type slightly. And the algorithm can actually learn about the differences in ryegrass between one soil type and another soil type. Okay, and that's some of the algorithms that are starting to come through, although again still computationally expensive. Temporal will be the holy grail, because temporal will mean I can actually learn how this weed grows as a function of time, and I can distinguish that at any particular point in time during its growing season amongst the crop. A very, very expensive, computationally expensive type of algorithm. So they're the two things that I just need you to keep in mind. Most algorithms are supervised, deterministic. The simplest of the lot. That's the ones that you're seeing over and over again every time you hear about machine learning or AI or whatever being applied to weeds. The holy grail would be unsupervised temporal machine learning. That will be the one where the bots out there or the tractors out there constantly learning about different things, and as they grow as a function of time and not worrying about any human supervisor coming through. So that's on machine learning. The second paper, if you're interested, is on a comparison of different types of weeding technologies that are used out there. It came out earlier this year. I've just got one graph. That's the only thing I want to show out of that one. And basically what the paper shows is for different types of non-chemical weeding technologies, how much energy is required in order to be able to use on farm and remove a weed. And you'll see different types of tech coming through, everything from laser cutting to laser units themselves, microwave, solar. There's a whole range of that. And the reason why I wanted to show this was because we hear a lot about chemical or herbicide use. We hear a lot about using less herbicides by being smarter. Mechanical weeding is a classic one. But what I wanted to bring up here was there's the researchers all around the world that are actually looking at a whole wide range of different types of weeding technologies beyond the chemical use and beyond just mechanical use. Okay, and there's lots of different techniques out there. And I'm going to come back to this later when we go to where to next. Okay, that was the academic part. Now we'll move back into some projects. So this is a project that we recently got from GRDC, which is around non-chemical weeding and aspects around that. The whole objective was not to just look at weeds on fallow or when the plants were small, but to actually look at what happens if you can detect and remove weeds even when the canopy's up high and covering the weeds themselves. So we kind of built a little unit just to play around with. It's like a little trolley unit. Inside the trolley unit is a sensor looking down into the crop, and you kind of push this thing along. This was just during the data collection phases. Push this along, collect lots and lots of data, and then you train up the algorithms. And what you see here is on the left is a camera unit looking, so inside that black box, the camera unit's looking down through the black box onto the ground. So on the left there is the camera unit looking down, and on the right is two different algorithms detecting the weeds amongst the wheat, okay, in that particular case. So it's being able to kind of detect it. What it's doing as it's going through is just pushing the wheat away, and being able to detect the weeds in between. So we put it on the back of that solar electric bot put underneath of the solar electric bot that I mentioned before, to just be able to give us that precision control that we're looking for as we're going down the roads and on the headlands. And the unit's now looking down as it's going through. So you'll see here as the bot's going down, it's detecting the weeds as it's going through amongst the wheat. Right? So the little red that you'll see on the right there is it detecting the wheat. And then we started to look at different types of crops and the different types of weed detection. So on the left here you'll see some weed detection on a wheat farm, and on the right there on a chickpea farm. And then we started to look at some tools. So one of the, we're roboticists, so we just muck around. We don't even know if this is the right thing to be doing, right? But you've got this thing going through. Now it's detected a weed, and it's a little grinder that comes along and just comes down and just rips the top layer of that weed. Now, if it's a weed that kind of propagates when you rip it apart, it's probably a problem, right? It goes everywhere. But, it's just us experimenting through that process. So it's now about detecting the weed and accurately timing the point where you can actually remove it without using the chemicals. So this is now it through the row. Okay, so you'll see it just coming through now, and just wherever it's detecting the weed, it's just kind of putting down the grinder and removing the top layer of that weed. A little schnoz out the front of it is just to help kind of pull the wheat apart as it's going through. So we'll be going now through, almost every month now is going through different commercial farms and just testing out the process as we go through. This is another one. The little white paper that you see is our make-believe farm inside our lab at the moment now. So all those little black squiggly lines are pieces of wheat, right? And then we get across some weed. And now we're just looking at some mechanical tines. So now it's detecting the weeds, and in real time then coming along and just being able to kind of, almost like a piano kind of process, just being able to isolate through that. The other piece of work that we're looking at is laser tech, right? So being able to just kind of zap a weed, and what does that look? This is probably not the right approach. We're not trying to burn a farm down or anything like that. So the whole idea is not to kind of zap a weed and kind of burn it from scratch. But in fact, you can actually, if you get the frequency of the laser right, you can actually pop the cells inside the plant without damaging the plant itself. So you basically kill the plant because you're boiling the cells basically internally. But it's about getting the frequency right of the laser unit when it's hitting the weed. So this is going to be something that's going to come through. It's at the moment now we've tried it out on different, on ryegrass and on turnip weed, right? So what happens when you have different size laser beams and you know, this is the Star Wars stuff, right? And the kids, you know, the PhD students love this stuff, right, at the moment now. But you've got different types of laser sizes. You're looking at the different types of weeds and you're burning them and you're looking at it against the control, right, whatever the control is. So this is ryegrass, dry weight over a certain period of time, and then what happens when you're actually hitting it with different types of laser units. This is the same thing on a control level. So what happens when you actually hit it and then leave it. So this is turnip wheat, okay? And what I want you to see is that at the moment now it's not really good technology. It takes about 2 minutes. You've got to zap it for 2 minutes before you can actually kind of boil the water internally. So now we're looking at 100 watt, right, which is a huge amount. It's a big laser unit, right? But again, just to have some fun, pushing the technology boundaries, trying to see where it's going. And as time goes on, the technology will get better. It'll get easier to use, and in fact, we'll probably be able to find the right frequency point to go through there. So where we're going with that GRDC project, we're looking at some more improvements to that current mechanical tool. The time implementation that I showed you before, that's going to come through as well, and we're still doing some laser analysis. They've also asked us, can we actually look at weeds between the individual plants and being able to remove the weeds between the plants, and ryegrass being the hard one that we're working on as well. Okay, last. It's just where to next. Where to next on the new tools. I mentioned before, there's a range of different technologies out there. We're looking at everything from solar all the way through to laser units. You've probably heard about the microwave implementations as well. So there's going to be a range of tools that are going to come through over the few years in terms of being able to look at non-chemical weeding technologies. I mentioned before about the algorithms and where the holy grail is, and there is a lot of work going on at the moment now. It's branching out into semi-supervised but into the unsupervised as well. Having a system go out there and constantly learn, and in fact being able to learn then not only the crop growth rates but also the weed growth rates as well. And I just wanted to end on this particular slide, and it's a bit messy, and I just wanted to walk through it because I think it's important, because when we look at robotics, so in my lab we've worked with Rio Tinto. So if you heard about all the autonomous working mine sites that you had there, all the autonomous drill rigs, haul trucks, including the operations, came out of my lab, and a lot of that technology is coming across into the ag space. But when you think about what automation does, what robotics will do on farm, it's more than just the weeding element, right? There's a whole bunch of things that it can do on there. But more importantly, it's the process of being able to collect that information and better decision making on farm that will then help the weeding. I'm just showing you this plot here, which is, if you go up the y-axis, it means a lot of uncertainty. And if you go along the x-axis, it's time. Okay? And this is a mine site operation, and I want to talk about a few things there. But if you could imagine, you've just got a new plot of land and you're going to start the process of farming on the land. So we're going right from the beginning and thinking through that whole process as we go through. But this is in the mining example. What the miners will do is they'll do some resource drilling, which means they'll get some information, lots of information, and then they'll just sit on that, waiting until the time is right to start to extract the ore body out. Then they'll do some core logging, so they'll get more information. Then they'll blast it all, those classic, blast dynamite processes they go through, so they lose all that information as it's going through. Then they'll do some face inspections, get more information. Then they'll put it on the back of the truck, lose information, etc. When we started adding automation and robotics into the process, all the information got a lot better. And what that meant was that they went from a production cost of about $60 a tonne down to $30 a tonne. So they halved the production cost process just by getting better decision making through having the system out there and gaining information. But more importantly, these red crosses are areas where they didn't need to repeat the process again, right? So they didn't need to actually come along and do those red crosses. They used to do that in terms of humans used to be able to do that. Now, with the robotics in place, they don't need to do that anymore. And the reason why I'm mentioning that is because a lot of the work that we're doing now with the grains activity on robotics and weeding is about how you would change operations in order to make the autonomy solution work better, but also at the same time make it easier to remove the weeds over the whole production cycle. So we're working with the ag guys over at the University of Sydney about when do you take out the bots, when is the right time to be able to do the weeding, when do you collect the information, etc. So there might be certain tasks that you don't need to do in addition to removing chemicals through the mechanical weeding process. So I'm leaving that. It's still early days, but what you're going to see as time goes on within this project is when is the right time to be able to take out the robotic solutions during that production cycle in order to remove the weeding costs and herbicide use. So that was the end of the presentation. Thank you for your time. I think I was told that if there are any questions, I can answer now or during the break. So thank you.